Hi, this is Mr. Wakefield again, looking at section 9.6 now. This is the section where we look at equations that have radicals in it. And we've seen equations with radicals in it before, but the difference is that these equations actually have a variable underneath the radical. That makes a big difference, okay? And what we need to do is kind of similar to the last section. In the last section, we had to get rid of the fractions because it was equations with fractions in it. Well, when you have equations with radicals in it, and in particular when the variable's underneath the radical, you want to get rid of the radicals. Okay, so if you've got an equation with a fraction in the equation at the beginning of the problem, you want to get rid of those fractions. And then if you've got an equation with a radical at the beginning of the problem, in particular if it has a variable underneath, you want to get rid of the radicals. So in each case, the last section with the fractions and this section with the radicals, you want to get rid of those things. And then what happens is that just like in the last section, after you get rid of that thing, in this case the radicals, but in the last section, after we got rid of the fractions, what happened? We ended up with either a linear equation or a quadratic equation. And that exact same thing is going to happen in this section. Once you get rid of the radicals, you'll end up with one of those two things. Let me just make it clear here, first of all, these are not linear or quadratic equations, even if they look like it. And the reason why is because you can't have a radical in a linear or quadratic equation if there's a variable underneath it. Just like I said in the last section, that if you have a fraction in your equation with a variable on the bottom of the fraction, that can't be a linear or quadratic equation either, even if it looks like it. It just can't be. Okay, so, but like I said just a minute ago, we're going to transform the problem into either a linear or quadratic equation. All right. Once we do that, just like in the last section, we will then be able to solve using our knowledge of linear and quadratic equation solving, all right, in order to solve the equation and finish it up. All right. Remember, though, also, just like in the last section, we do need to check our answers here. Okay, so we need to check our answers when we have fraction equations, but you just have to check the denominators to make sure that they're not zero. All right, we did that in the last section. We found out that sometimes it led to a bad answer that we had to throw out, and so that's why it's so important to check. All right, same thing here, only now we don't check the denominators because there's not going to be any denominators. All right, but we do need to plug the thing back into the original equation. I'll show you that, okay, as we go along here. But we do need to check our answers with fraction equations and radical equations too, okay, where the original problem is a radical equation, all right? So let's get started here. How do we get rid of this radical like I was talking about? You want to rewrite the equation so that the radical term is alone on one side of the equation, okay? You can see here that it's not, okay? Remember, a radical term is when you have a radical and then times something usually in front of it here. There's an invisible 1 in front of this. So this right here is the radical term right there. It's not by itself, is it? The minus 2 is not part of the radical term. The reason why it's not part of the radical term is because it's being subtracted with the radical term. All right. Remember, again, if the 2 is being multiplied by the radical term, then that would be part of the radical term. All right. Just like here, the 4 is a part of the radical term right there because the 4 is being multiplied by the radical. All right. The 2 is not here, though. It's being subtracted. So it's very important that you do not move on to the next step. Believe me, it'll completely mess things up if you do move on to the next step. You have to get the radical term by itself. Okay. So how do we do that? Just like we did back in the section where we were doing square root property, all right? You have to take the thing that you're trying to get by itself, all right? Here I was trying to get z squared by itself and pretend like it's a variable. And then whatever steps it took to get that pretend variable by itself, you get that z squared by itself, and it looks almost exactly the same here. It's the same idea here right now. This box is what I want to get by itself. That's the radical term. Okay, so I'm going to pretend that that's a variable again, just like we did in the square root properties section. How do I get that variable by itself if it's m minus 2 equal to 3 right there? Well, this is a linear equation now, okay, because I changed it to an m. And so we know that we need to get, since it's a linear equation, we know we need to get the 3 and the 2 on the same side, and we get m equal to 5, right? And I got m by itself. So just like I got m by itself, I can get the radical by itself, since the radical and the m are basically the same thing here. I can get the radical by itself with the same step, adding 2 to both sides. And then the 2's cancel just like they canceled over here. And we end up with the same thing. We end up with 5 on the other side, just like we ended up with 5 on the other side here. Okay? So we did it. We got the radical term by itself. All right? What do we do next? It says square both sides. Again, if you square both sides without getting that radical term by itself, like I said, it's going to mess everything up. It's very important you do that first step before you square both sides. Here's how you square both sides. You need to put a parenthesis around the entire left side of the equal sign and the entire right side. That's to make sure that you square everything on the left side and everything on the right side. Okay. You got to treat it like it's a parenthesis here. All right. When I say everything, I don't mean every little part separately. I mean you treat it the same way you would, all right, as if there's a parenthesis here. That's why we have to put the parenthesis there. And you know that when you have a parenthesis with an exponent outside of it, it means that you are taking that entire parenthesis to that second power. Now, we learned, since we just have a radical inside of that parenthesis right there, we learned about what that means back in when we were rationalizing the denominator, and we had these problems, you know, where we had to multiply by that same thing on the bottom, but we changed the sign in the middle. Anyway, we ended up getting square root of 5 squared on this problem, square root of 7 squared. But what does it mean when you square a square root? That's my question right now. What does it mean to square a square root? It's just equal to the inside, right? We talked about that. As long as there's not a negative number on the inside, okay, here, that works. And you're not going to need to worry about that here in this current section that we're doing. Even if there's like a minus sign in there, that's okay. All right, it doesn't mean the whole thing's going to be negative, so don't worry about that. The point is that it just becomes the inside of the radical. The radical and the exponent cancel each other out, in other words. Okay, assuming that this is a square root radical, okay, which it will be in this section. We're just going to be dealing with square root radicals in this section. So the square and the square root cancel each other out, and we get y plus 7. On the other side of the equal sign, we square that too, and as you can see, 5 squared is 25. And so you see what happened here? We got rid of the radical, and we have a linear equation. That's what's going to happen every time. You're either going to have a linear or a quadratic equation after you get rid of that radical. We then solve it accordingly. Since this is linear, I'll use my linear rules. And that means to move the 7 and the 25 to the opposite side of where the y term is. And we get y equal to 18. Done. Don't circle that yet, though. Remember, we have to check our answers. Okay. When do we check our answers? When you have fraction equations and when you have radical equations, right? So I want to check that 18. How do I do that? I simply plug it into the original equation. Don't plug it into any of these equations down here. The original equation. It has to be. Okay? So replace the variable with an empty parenthesis and then put the number that you're checking inside of it. That's what I'm doing here. Okay? Anytime you plug a number into a variable, you use that empty parenthesis, put the number in there, okay? That's how you plug it in. Now we do order of operations, and order of operations, what it is, in this case with the radical, we do order of operations on each side, by the way, like we've done in the past in order to check to see if these two things truly are equal to each other, okay? Because there's no variables here, and we're just trying to see if it's true. So we want to do order of operations on each side. This side obviously is 3, okay? There's nothing to compute there. But when you have a radical, remember the inside of the radical is kind of like the inside of a parenthesis. All right, it works in the same way, where you got to do that first, just like you do the inside of a parenthesis first. So what would that be? That'd be 25, right? 18 plus 7 is 25. Then you have to compute the radical right after you figure out the inside of it. Okay, you can do that. But definitely do it before you add or subtract. In this case, subtract. All right. So again, PEMDAS. All right. But the inside of a radical is like the inside of a parenthesis. That's why we do that first before we do any of this other stuff, multiplication, addition, subtraction, any of that. But you got to figure out the radical right after you figure out the inside of the radical. So you're kind of still in the parenthesis category there until you figure out what that radical is, which is 5. And then we subtract, and you can see that this is true. 3 is equal to 3, right? Since it's true, what do? Just like in the last section, if there's no issues, all right, and it's true, we circle it. If there's an issue, in other words, if it's false, okay, then you would cross it out, similar to the last section where we crossed it out if it was a zero denominator, okay. So it all comes down to whether or not these two things are equal to each other when you figure out what each side of the equal sign is equal to. Okay? But don't forget to do that check. You can see here in this problem that we have two radical terms, one on each side. All right? This is just a radical. This is a radical times a regular term outside of it. So these are both radical terms. It's okay to have more than one radical term. What's important is that at least one of them is alone on one side of the equal sign. Well, both of these are alone on each side of the equal sign. There's nothing else other than this radical term here. Okay, again, the 4 is included in that because it's being multiplied by the radical, and then this radical term as well. So when that happens, when you have a radical term, one on each side, but there's nothing else on each side other than just those radical terms, then what you do is you just immediately square both sides right now. Put your parentheses there. Don't forget that. Okay. We know that when you square a square root, it's just equal to the inside, right? The square and the square root cancel out. However, what's the deal with this, though? See, there's a problem here because there's a regular term outside of that. So do we have to square that 4 also? Yeah, we do. And there's multiple ways to do it. When you have a radical term with an outside part, okay, like 4, any outside part, okay, here there was nothing outside the radical, so that was different. But any outside part at all, you gotta, the easiest way to do it, I think, again, there's multiple ways to do it, but when you have an outside part right there to the radical term and you're squaring the entire radical term, what I do is I just multiply them. I just expand it out here where I multiply it twice, because that's what the exponent 2 means. Okay, and the reason why I do that is because we learned back in the radical chapter that when you multiply a radical term times another radical term, you multiply the outside times the outside, and you multiply the inside times the inside. But the outside times the outside stays outside of the radical, and the inside times the inside, 3 times 3 is 9, that stays inside of the radical. And then we then figure out what the radical is equal to, or simplify it if we can't figure it out. But this is a perfect square number, so we can figure it out. That's 16 times 3, isn't it? And that's equal to what? 16 times 3 in your calculator will be equal to 48. And so this whole thing right here is 48. So that's a pretty short problem right there. We already got A by itself, just like that. Okay. But what do we do after we get the variable by itself and solve for it? We got to check it, right? Plug in the 48 into the A here. Now, how do you figure out? See, notice that we can't do any order of operations here. You can't do 4 times 3 because you can never do the outside of a radical times the inside of the radical. There's nothing to compute here because we don't know what the square root of 48 is. We know what the square root of 49 is. We could have done that, but we don't know what the square root of 48 is. So when you have two radical terms like this and you want to know if they're equal to each other, The best way to figure that out is to simplify both of them, if possible, and see if they come out the same. Okay, this is already simplified because you can't break down the 3 at all. All right, the smallest number that you could factor out of any square root radical is 4 from the perfect square list, and that's how you simplify square root radicals, is by looking at that list. So that's done. But over here on this side, the 48, you can factor out a 16 out of that, can't you? And if I then figure out what the square root of 16 is, sure enough, these two things end up being equal to each other, don't they? So this is true. Just like over here, 3 and 3 were equal to each other. These two radical terms are the same also. It's true, and when it's true, we circle that thing. If it had been false, again, like I said, we would cross that out, and if there's no answers left, we would say no solution. Okay. We'll see that coming up. Problem C. Again, you can see here in problem C that the radical term that you have is by itself. Notice there's nothing outside of the radical. Okay, nothing at all, and so it's definitely by itself. It's when you have a radical term, in other words, a radical or a radical times something, and it's being, say, for example, subtracted with something like -2, or like in problem D, you've got a radical term and it's being added with a term like +2. That's when you got to do that first step before you square both sides, okay, before. That's when it's really important to do that. But anyway, put a bracket around both of these things. It's now time to square both sides. We know that when we square a square root, nothing outside of the square root this time, but just the square root, it's just equal to the inside. This right here is just simply y squared, isn't it? Okay, because it's just y that you're squaring. Okay, so I got rid of the radicals. What happens when I get rid of the radicals? All right, you either end up with a linear or quadratic equation. This looks like it's quadratic because of the y squareds, but it's one of those rare things where it looks like it's quadratic, but if you try to put all the terms on one side, which is what we oftentimes will do, in fact, you'll notice throughout the rest of this worksheet packet that usually if a quadratic equation pops up, not at the beginning, not the original problem being a quadratic equation. I'm talking about when you suddenly get a quadratic equation in the middle of the problem. We saw that in the last section here where it suddenly popped up in the middle. Usually when that happens, usually you'll be able to do the factoring method from section 7.5. I'm not saying you have to. As long as you're sure you know what you're doing and you know a different way to do it, okay, like I said, when you see a quadratic equation in the middle of a problem, it will be your choice. As long as you can get the right answer, okay, it's your choice on how you get to it, all right? When I say it's your choice, and you still have to use one of those 4 methods. That's what I mean. One of those 4 methods that I taught you, not some other thing. Not that there is any other thing that I can think of, but you never know. But you can use any one of those 4 methods to solve that. Okay. So yes, the factoring method usually will work though when you get a quadratic equation that suddenly comes up in the middle of the problem. So that's what I'm thinking right here. And so I'm thinking, oh, since I need to do the factoring method, I need to move all the terms on one side. But if I tried to do that, what's going to happen here? The y squared terms cancel on both sides, and there's no more y squared terms. What does that mean, you guys? That means that it's now a linear equation because there's no more y squared. So just because something looks quadratic doesn't mean it stays that way when you put the y squared terms together. That doesn't happen very often, okay? But sometimes those y squared terms cancel out, and you just end up with y to the first power, okay? So since now y to the first power is the largest exponent here, you don't have y to the second anymore. It's a linear equation. And so I then need to use my linear rules, which is to get the 0 and the 9 on the same side here. Okay, and now y is by itself. So what's the last thing I got to do after y is by itself? I need to check my answer. Okay, I'm going to check y equal to -9 by plugging it in. Plug it in wherever you see the variable in the original equation, not where that does not include the squares here. I put those in afterwards. Okay, it's the original equation before I square both sides. Very important there. That does make a difference. Okay, it's got to be the original equation. And there you go right there. So this side on the right is definitely -9. There's nothing to compute over there. But is this side also equal to -9? Let's find out. Remember, you got to calculate the inside of a radical before you can calculate the radical, like we saw up here in this problem. So on the inside of the radical, I have an exponent, and I have some addition, right? Exponents come before addition, as you know. We have 81, and then the other things here, plus -9, plus 9. Okay. What is 89 plus -9? That is 72. What is 72 plus 9? That is 81. Okay. What is the radical, square root radical for 81? No, it is not -9, right? Remember, we said that a square root radical with nothing outside of it at all, it's just the radical only. As long as you have a positive number in there, if it was negative, there would be no answer underneath here, the radical. But if it's a positive number underneath there, remember we said that a square root radical is always equal to the positive square root. Okay, so the radical 81 is equal to the 9. It's not equal to -9. Okay, it's just equal to 9. Yeah, remember when we had when we first learned about radicals? Why is this only equal to 7? It's not equal to -7. It's not equal to both 7 and -7 at the same time. No. It's just equal to 7. That's because a square root radical with nothing outside of it is just equal to the positive square root of 49. Okay, so that's why the left-hand side right here is just equal to 9. So this is false. And what happens when it's false? We go back and we cross that out, and we saw something similar to this in the fraction equation video that we just did, okay, where if you have only one answer and it's not good, okay, in this case it was because the denominator was 0. In this case it's because it's false. In either case, you need to cross it out, and if it's the only answer that you had to begin with, then you say no solution. So let's say that here. Sometimes you'll get two answers, and one of them will be good and one of them will be bad. You'll see that coming up here. All right. But if you have nothing left after you've checked your answers, that's when you say no solution. Okay. But if there's still one good one left, then don't say no solution, because there's still one that's good. All right. You have still one solution left. Again, we'll see that coming up. But before we see that, what I'd like you to do right now is please try 1, 2, and 3. 1 on the first page here, and then 2 and 3 on the second page. Try those first, and then we'll look at those last set of problems there, which are a little bit more involved. Not too much, but a little bit more involved. So let's do these problems first. 1, 2, and 3. Hit the play button after that, and then we'll take a look at those answers before we move on to that last part. Okay, number 1 here, since we have a radical term by itself on one side of the equal sign, we are going to square both sides right now. You don't need to move any terms first, all right? And so we got what here? We've got squaring both sides. Again, put those brackets there to make sure you get everything squared on each side as a group. Because you're not allowed to square things separately. You can't square the x and square the -12 separately, okay? You got to square it as an entire group in the parenthesis there. And when you square a square root, if it's just a square root on the inside of the bracket, when you square that, as we now know, it makes the radical just disappear. The radical and the exponent cancel each other out. The other side, as you can see there, we got 16. This is now a linear equation. There's no x squareds there. It's just x. And so we move the 12 and the 16 together. We get a final answer of 28. Why did I circle that? Well, I only circled it after I checked it. Okay. I know it's the circle is up here and the checking is down here, but I did not circle it when I did this problem until after I checked it. Okay, so don't forget to check. So I plugged the 28 into here. You can see that down here. And then I figured out what this side was equal to see if it was equal to the other side, which is already equal to 4. And you can see that if you figure out the inside of the radical first, and then you calculate the square root, it does indeed end up being equal to the same thing, 4 equal to 4. Since it's true, we circle it. Next problem. Number 2. Just like we saw in problem B on the first page, we have just a radical on one side, and then we have a radical term with something being multiplied by the radical on the outside there. Okay, so we square both sides since both sides have just a radical term and nothing else. All right, this obviously is going to be equal to 17x minus 4. You're just squaring a square root. But when you square a radical term that has an outside part like 4, okay, again, it's easiest just to do it this way, I think. Outside times outside stays outside, 16. Inside times inside, x times x is equal to the inside here. Keep the x squared on the inside. But then figure out what that radical is equal to, or simplify it if it's not a perfect square. But x squared is a perfect square. X squared, x to the 4th, x to the 6th, x to the 8th, those are all perfect square terms. Okay, we know that the square root of x squared is x, okay, because x is the thing that you square to get x squared, all right? And so we end up with 16 times x because the radical is equal to x here. So 16x then is what the right-hand side of the equation is equal to here. All right. This is another way that you could write it here. Okay, you don't have to do that. You could just do it this way. But I wrote that additional thing here for just to give you an additional perspective there. But you can do it this way. So we got a linear equation now here, don't we? Okay. And so I need to move the x terms to the opposite side of where the negative 4 is because the negative 4 doesn't have the variable in it. Okay, variable terms on one side, the terms that don't have the variable in it on the other side. I then divide out and I get x equal to 4. But again, I checked my answer in the original equation before I circled this. And so why did I circle it? It's because it ended up being true. 8 on one side and 8 on the other side. It's true. Okay? And that's why I circled it. All right? Number 3. By the way, multiplication before subtraction, right? 68 minus 4, that's where I got that from. Okay, and then here you got to compute radicals before you do multiplication. So the radical was equal to 2. 4 times 2 also is equal to 8. Finally, number 3. Both sides have a radical term, so we square both sides. Neither radical term has anything on the outside of it, so the square and the radical just cancel each other out, and we end up with 5y plus 2 equal to 3y plus 8. We then realize that this is a linear equation, and so we need to move the y terms to one side. I moved them to the left, and then we move the 2 and the 8 over to the right. Okay, because they got to be on the opposite side. If you do that, you end up getting 2y equal to 6. Okay, and then 2y equal to 6, you can then divide out, and your final answer is going to be y equal to 3. And again, I only circled this after I checked it, and when I checked it, even though I don't know what the square root of 17 is equal to, okay, clearly the square root of 17 and the square root of 17 are going to be true because they're the same thing, right? Doesn't matter if we don't know what square root of 17 is equal to. Obviously, these two things are the same thing, and so therefore they're equal, and therefore it's true. Okay, so you don't need to know what square root of 17 is. All right, you just know that the two sides are the same, and that's the important thing. Okay, try to figure out what the radical is equal to if you can, but this is not square root of 16. This is not square root of 25. It's square root of 17, so we can't figure it out. Okay, but we just know that it's true because they're the same thing. Okay, so that is 1, 2, and 3. Let's go back to the first page now. And let's look at those other problems, which are a little bit bigger, but not too much bigger. But problem D. Problem D is very similar to problem A, the very first problem that we did here. Where you have what? You've got a radical term being added, not subtracted like this one, but being added. But still, the fact that it is being added to the radical, that makes the plus 2 separate from the radical term. It's not a part of the radical term when it's being added to the radical or being subtracted from the radical like the minus 2 is here. Okay, it's when you multiply a radical by something that thing on the outside that's being multiplied by the radical, that thing is a part of the radical term. All right. So the 4 is a part of the radical term, but the plus 2 and the minus 2 are not. So we need to get the radical term by itself, and the plus 2 is not a part of that. All right. Again, you can do the same thing, and you don't have to write it down if you don't want to, but as long as you can visualize it and understand it, you know that in order to get this thing by itself, we pretend like that's a variable. Okay. And I know that gives me 2 variables here. So when we make we pretend like the m is the box here, what we do is we realize that there's 2 variables here, but we need to get the m by itself. How do we do that when there's 2 variables? We saw something like this before back in section 4.4 when we had y and x, and we needed to get the y by itself so that we could do that slope-intercept form thing. Okay, what we did was we pretended like the x was a constant term. We pretended like it was a term that didn't have the variable in it, even though x is a variable. Because since the y was the thing that we wanted to get by itself, all right, any other variables, we just thought of those the same way as we thought of the terms that don't have any variables at all. Okay, so the 4x and the 18 were similar. They were the terms that did not have the variable in it that you were trying to solve for. And so we moved them to the same side. Okay, again, no different than if you had no variable here at all. All right, because it's, again, the goal is to take the variable that you're trying to solve for, get that term that has it by itself, okay, get that term by itself, 3y, and then divide out. All right, but the terms that don't have the variable in it that you're actually trying to solve for, okay, those are treated the same way as the terms that don't have any variables at all. All right. So you want to get the term that has a variable that you're trying to solve for on one side of the equal sign and all the other terms on the other side. And it's the same exact thing here in this problem. It's the m that we want to get by itself because that represents this box that we're trying to get by itself. And so the fact that there's a different variable, that doesn't matter. All right. We want to get the m on the opposite side of where the 2 and the k are. And we know that since there's no parentheses here, we just add or subtract the 2 over in order to get the k and the 2 on the opposite side of the m. But k and 2 are not like terms, are they? So we have to have a plus or minus still separating them since they're not like terms. Okay, we can't say 2k. We can't say negative 2k. All right, we've got to have a plus or minus in between them. And since k is positive and 2 is negative, all right, we have a positive k and then the minus in front of the 2 because the 2 is negative. All right, so be careful not to combine these. All right. It's k minus 2. I've seen a lot of students say 2k or negative 2k, and it messes up the whole problem. Okay, these are not like terms. So in the same way, when you move over the 2 here, you get the radical by itself, just like the m was by itself, and then you get k minus 2 right here. All right. Now that I have the radical term by itself, I now what? I now square both sides, use your parentheses around the entire left side of the equation with the 2 on the outside, and a parenthesis around the entire right-hand side of the equal sign with the 2 on the outside. And we now know that when we square a radical, it's just equal to the inside of the radical. The radical disappears. But what's the deal with this? Okay. We've seen that multiple times this semester, including the very first day of class. All right. When you have a parenthesis with two regular terms in it, no radical terms this time, but just two regular terms in it, with a plus or minus in between them, okay, with the 2 on the outside, the exponent 2 on the outside, we know that we have to do it like this, where we write the bracket twice because it's being multiplied twice. Okay, same thing here. We need to do what? We need to do k minus 2 and k minus 2, like that. What is that equal to? And I need to make some room here, hold on, to get that answer in there. But if I multiply k minus 2 times k minus 2, I'm going to get what? I'm going to get k squared minus 2k minus 2k. Again, this is from section 6.3 on the first day of class, and then plus 4 there. So let's write that down. K squared minus 2k minus 2k plus 4. And once again, like always, you guys, when we get rid of the radical, we either end up with a linear or quadratic equation. Since we have a k squared right here, and it's not going to cancel out like it did in the last problem, okay, there's not another k squared here that's going to cancel with it. Okay, this is definitely going to be quadratic. Okay, and like I said, usually, although it's your choice, usually when you see a quadratic equation suddenly pop up in the middle of a problem, the factoring method is easiest. But it's up to you what you want to do. You have the choice here. As long as you use one of those 4 methods I showed you. Okay, any one of the 4. Okay, so what do we got here? K squared minus 6k minus 7 when I move all that. Why am I doing this? Why am I moving all the terms to one side? It's because that's what you do in the factoring method, right? But we want to keep the k squared term positive. Like we said, when we do the factoring method, we want that k squared term to be positive, okay? Because especially if it comes out as where you have a k squared term and a k term and then no k at all in the last term, that's one of those Berry method things, and the Berry method thing only works if it's a positive k squared term, not a negative k squared term. Okay. So let's do the Berry method. 1 times negative 7 is negative 7, and what 2 numbers add up to negative 6 in the middle right there? Well, that would actually be 1 and negative 7, wouldn't it? So factoring that, we get k minus 1 and k minus, k plus 1 and k minus 7. Like that. Okay. Set those equal to 0 there, and we get k plus 1 equal to 0 or k minus 7 equal to 0. What 2 answers do we get out of that? Well, these are both linear equations now. All right. And so we need to move the 1 over on this one, and we need to move the negative 7 over on this one. Subtracting the 1 over, I get k equal to negative 1. Don't need to divide out. The k is already by itself there. And then on this one, if I add the 7 over, I get k by itself equal to 7. So I got k by itself on both of them. Great. But what's the last thing I got to do? In a radical equation, I have to check my answers. Since I have 2 answers this time, you guys, I need to check them separately. Do not try to plug them both in at the same time. That's not how you check answers. You got to do one at a time if you have more than one answer. So I'm going to start out with negative 1 and see how that works out. If I plug in negative 1 into the original equation like I'm supposed to do, I get what? Let's find out. Again, the right-hand side is clearly equal to negative 1, but the left-hand side, we have to figure out the inside of the radical first. All right. 2 times negative 1 is negative 2. Multiplication before addition. So negative 2 plus 11 is 9. After we figure out the inside of the radical, we have to calculate the radical before we can add. The square root of 9 is 3, and so we end up with this. Is this true or false, you guys? Well, this is false, right? Okay. 3 plus 2 is 5, and 5 is not equal to negative 1, so what do? That means that we cross out that number that I just tested, but that does not mean it's no solution. We still have to test this one. This one might actually have a solution. Okay? So let's see if it does. K equal to 7. If I check that one, I get, again, plugging it into the original equation. All right. I get this right here. True or false? Let's find out. The inside of the radical goes first here. Multiplication goes before addition, so it's going to be 14 plus 11. 14 plus 11 is 25. All right, and then you have to calculate the radical before you can add. And so the radical is 5, and 5 plus 2 equal to 7. That's true, isn't it? Okay. So what do we do when it's true? We circle that one, don't we? So in this particular problem, you got one bad one and one good one. Circle the good, cross out the bad. Circle the good, cross out the bad. You only say no solution if the entire problem is no solution. Okay? In other words, all the answers were bad. But since one of them was good, circle the good one and just cross out the bad one. All right? Problem E is very similar. And then I'll let you guys try some on the second page there. But again, you have a radical term being subtracted with a different term there, not being multiplied by it. So the minus y therefore is separate from this radical term, and therefore I need to move that minus y over. Okay. As we saw in the last problem, okay, when you have a radical term that's being either subtracted with a term or being added with a term, like in this last problem, okay, the way that you move it over is by what? Okay, is by adding or subtracting that other term that is separate from the radical over. Okay, so since this was plus 2, the 2 is being added to the radical, we subtracted it over. Since the y is being subtracted out, though, since it's being subtracted, we're going to add it over. Just like I did in problem A up here. Okay, see up here we had the radical minus 2. And so I had to add the 2 over. Same thing here. You've got the radical minus y on one side of the equal sign. The radical being subtracted with something, just those two things on one side of the equal sign. When that happens, just like in problem A, you take that thing that's being subtracted on the outside of the radical and you add it over. That cancels the y's over here. But what's 3 plus y equal to, you guys? Remember, those aren't like terms, so the plus has to keep it separated, all right? So you could say 3 plus y. Let me write down the radical first since it's now by itself. But you can say 3 plus y, or you can say y plus 3. It doesn't matter. Remember, you can reverse around the two terms that are being added or subtracted as long as you have the correct sign in front of each term and as long as you have a plus or minus in between the terms to keep them separated since they're not like terms. They're both positive, so I have positive y, positive 3 with the plus in between. Okay, and so that's correct to write it like that. Since the radical is now by itself, we square both sides. The radical cancels out because it's just a radical being squared, like we've seen a number of times now. But again, this is very similar to the last problem, isn't it? What makes it similar? Two terms here. When you got two terms with a plus or minus in between them, you have to do this thing right here, just like with the k minus 2. Okay? Remember, this is different than, say, right here. Why did we not do that same kind of thing here? Actually, we kind of did. We did write out the bracket twice, but we didn't multiply it in the same way. Okay, that's because this is a single term here. There's no plus or minus in between the 4 and the radical 3. All right, so you did the multiplication completely different. But when you've got two terms with a plus or minus in between it, like we do with k minus 2 or with y plus 3, that's when you do this thing from the first day of class where you got to go y times y and y times 3, and then 3 times y and 3 times 3. Okay, it's all because there's two terms inside that bracket with the plus or minus separating it. What are those four multiplications equal to there, you guys? They are equal to y squared plus 3y plus 3y again, and finally plus 9. And as you can see, once again, very similar to the last problem, this is going to be quadratic. And which means that since it popped up in the middle of the problem, usually, and this is no exception, factoring method should work fine here. That means that I want to move all the terms to one side so that I can, because that's what you do in the factoring method, you move all the terms to one side. So you have a 0 on the other side. You don't factor until after you got that 0 on one side. These three terms combine together to be minus 4y. These two terms combine together to be plus 3. Okay. And then 0. What does this factor down to be right here? This factors down to be, according to the Berry method, 1 times 3 is 3. And what two numbers add up to negative 4 from that? Wouldn't that be negative 1 and negative 3? Like that. And now that I have done factoring, the last step of the Berry method doesn't need to be done there because it's not going to change anything there. We end up getting y minus 1 equal to 0 or y minus 3 equal to 0. Like that. Then what? Then we move since these are now linear equations right here, we move the 1 and the 3 over to the other side by adding the 1 over, adding the 3 over, and we get 1 and 3 as our answers. But don't circle them yet, right? You got to check them. Remember, when you get two answers, check one at a time. Starting out with the 1 here, let's see what I get. I get 3 is equal to 10 times 1 plus 6, like that, minus, and then you plug in the 1 there. So is this side equal to 3 over here? We already know this side's equal to 3. Again, you got to do the inside of the radical first. 10 times 1 is 10, plus 6 is 16. Then you calculate the radical before you subtract. The radical is equal to 4, and yes, 4 minus 1, we know that that's equal to 3, right? True. I'll go ahead and circle that in a minute. Let me go ahead and check the other one though first. Y equal to 3. Let's see if that one's true. Again, I'm plugging it into the original equation. So I got 3 equal to 10 times, the square root of 10 times 3 plus 6. And then plug in the 3 over there as well. Let's write that down. 3 is equal to the square root of 10 times 3 plus 6. Plugging in this 3 right here wherever you see the variable. The variable is in two spots here, right? It was here and it was here. And so that's why the 3's are now there. Calculate the inside of the radical first. 10 times 3 is 30. 30 plus 6 is 36. Then you calculate the radical before you subtract. The radical is equal to 6. And check that out. This is also true. That happens sometimes. Sometimes you get two answers and they're both true. All right, and the last problem, only one of them was, but here they both are. Since they're both true, I'm going to circle them both all at once here. You can circle them separately if you want to. That's fine. Okay, you can have two separate circles there. As long as you circle the good answers to make it clear to me that you understand that they really are correct and that they're not the type of answer that you have to cross out or something like that, that's what's important. Okay. We have two more problems on the back. They're very similar to the problems we just did. Problems 4 and 5. Okay, on the second page. Okay, that's what I meant. On the second page, please do 4 and 5. You can see here that we have a radical term being added to a regular term. Here you have a radical term being subtracted with a regular term. So just like we said, okay, when it's being added to the 1, you subtract the 1 over to get the radical term by itself. When you have a radical term being subtracted with x, then you add the x over, right, in order to get that radical term by itself. So that'll get you off to a good start there. But go ahead and finish that up, hit the play button, and then we'll wrap up this section. All right, number 4. Again, we need to move that 1 over by subtracting it over. But remember that 2t minus 1, those are not like terms. And so keep them separated, 2t minus 1. Don't combine them into one term. That minus has to keep them separated right there. All right. And so now we have the radical by itself, so we square both sides. All right. And so put a bracket around the entire left side and the entire right side. Okay, that reminds you that this is one of those problems where you write it like this. Okay, that's one of the reasons why that bracket is so important. It's not the only reason. We should do it all the time, but that's a big reason. Okay, that bracket reminds you that it's a problem like this right here, as we saw in 6.3. So we don't just square the 2 and square the t and square the negative 1 all separately. No. We put a bracket around that. We square it all as a group, and that reminds us that it's like this. Anyway, let's go ahead and finish that up here on that step. All right, we multiply that out. We get 4 different multiplications just like before. This right here, the radical just cancels out, as you guys know. We get 4t plus 13. They're going to cancel in the next step. That's why you see those cancel marks right there. But that is 4t plus 13. This is a quadratic equation. And so I'm going to move all the terms to one side like I said before. There is a GCF right here, as I now need to factor this, since I'm going to do the factoring method. It's 4. I then do the Berry method on what's left over. 1 times negative 3 is negative 3. The two numbers that are going to add up to negative 2 in the middle right there are negative 3 and positive 1, which is why I have the minus 3 and plus 1 in there. I then set these 3 things equal to 0. Remember, when you have a GCF and 2 brackets, you set all 3 of them equal to 0 in the factoring method. Okay. But since the first one does not have a variable and it's false, that's no solution. We've seen that before. Yes, it's okay to say no solution right there, even though there is going to be a circled answer over here. Just don't circle that. It's okay to say that just to represent this little equation here. Just don't circle it, because then I'll be wondering, are you trying to tell me that there's no solution for the whole problem? Okay, when there's really a solution over here, then it'll be, your answer will be confusing. I won't know which answer you're really saying is correct. So don't circle no solution, but you can say that there if you want to. Or you can just cross this out if you know that there's no solution there. But we still need to solve these other two. Because remember, when you do this thing right here where you set these 3 things equal to 0, these are 3 independent results here. Okay, all 3 of these. So if one of them gives you no solution, that does not invalidate the possibility that these could be solutions. They could still be solutions. And so moving the 3 over and moving the 1 over, I get 3 and negative 1. So when I checked my answers, I ended up finding out that the negative 1 was bad, but the 3 was good. All right, you can see how I figured that out here. Plugging in the negative 1, I got negative 4 plus 13 is 9. Square root gave me 3, but 3 plus 1 does not equal negative 2, does it? Okay. But plugging in 3, we got 12 plus 13 inside the radical. Ultimately, after figuring out the radical, we got 5 plus 1 equal to 6. And yes, that is true, isn't it? So that's why I circled 3. I crossed out negative 1. Okay, so we ended up with just one answer there. All right. Finally, number 5. Let me go ahead and move up there. Like I said before, we have to move the x over by adding it over since it's being subtracted from the radical term there, separate from the radical term. Remember that 4 plus x, those are not like terms, so make sure to keep plus or minus in between them. All right, you could either say 4 plus x or x plus 4, but do not say 4x, okay, because that would be making it into one term. Okay, since they're both positive terms, we're gonna, if you want to reverse it around like I did and say x plus 4, you just make sure that it's positive in front of each term there, and make sure that since the 4 is positive, make sure there's a plus in between the terms, okay, to keep it separated since they're not like terms. And since we now need to square both sides, we got to put brackets on both sides. And having those two terms with the plus in between it inside of this bracket, remember that means that when you square it, you got to do this thing, just like in the last 3 problems that we've done here in this section. Multiplying that out, we got these 4 different possible answers here, or 4 different answers. I went ahead and combined like terms on that. 4x and 4x gave me 8x. You don't have to do that. You could just bring these terms down. They're eventually, those 2 terms right there are going to combine anyway in the next step. So it doesn't matter if you do it now or on the next step. I did it earlier this time. But speaking of the next step, this is a quadratic equation now because of that x squared right there. So I decided to do the factoring method like I was talking about before. And that means that I move all the terms to one side and I get this right here. Remember to make sure that the x squared term is positive, okay, when you're doing the factoring method and you're moving all the terms to one side. That's why I decided to move the terms to the right-hand side instead of it over to the left-hand side. I then factored it using the Berry method here. Okay, 1 times -8 is -8, and then these 2 numbers are the numbers that add up to -2 in the middle there. So I plugged that in, -4 and +2 here, okay, and it gives me these 2 brackets. I then set those brackets equal to 0, and it gives me 2 linear equations. I solve those, and I get 4 and -2. You don't need to do this stuff over here. That's just an alternate way of factoring it here with the grouping method that we talked about a little bit back in the factoring chapter. Okay, you can just do the Berry method if you want. Anyway, checking my answers, I ended up finding out that both of the answers were true. As you can see down here, the work that I did. Okay, 40 plus 24 gives me the 64. The radical gives me 8. 8 minus 4 is 4. A similar thing happens over here. I'll go ahead and let you take a look at that here. Okay, but I plugged in the numbers into the original equation, and the original equation ended up both being true. And so therefore I circled both of the possible answers. Okay, so once again, you guys, remember, check your answers when you're solving a radical equation, if the original equation is a radical equation, that is, and also if the original equation is a fraction equation. Okay, that's the 2 times when you check your answers. Okay, when the original equation is a fraction equation, or if the original equation is a radical equation. All right. What I'm basically talking about there is that the reason why I keep on saying the word original is because, you know, sometimes you see a radical pop up like near the end of the problem, or maybe a fraction does at the end of the problem, or maybe even in the middle of the problem. Okay, I'm not talking about those equations. I'm talking about the original equations having radicals or fractions. Okay, so anyway, let me know if you have any questions about this in 9.6. But in the next section, we'll be moving on to something a little bit different, but it has some similarities to it. But again, let me know if you have any questions about all the different 1-variable equations that we've solved so far. Have a good day, take care, and we'll see you back here for the next video.